We are excited to be having Dr. Halpern here with us. And I'm going to be introducing him very shortly. He's coming to us from Philadelphia. Just a quick reminder before we begin, you can join us on Zoom these days for events every 2 weeks like this. And to get that login information, you can join our meetup group at meetup.com/CFL Freethought and look for more educational and social events happening online these days. In 2 weeks, we'll be joined by Rachel Deitch from the American Humanist Association. She is their Director of Policy and Social Justice, and she will join us for a conversation and Q&A session on humanism and social justice. We're really looking forward to that on September 20th at 3 p.m. Eastern. Of course, we're going to continue to stream these talks as YouTube events. You can follow us on YouTube at youtube.com/CFL Freethought. So if you miss it or you want to come back and see it later, you can definitely come back and see it there. We are continuing as the Central Florida Freethought community to do our socially distanced social events online. So we have Freethought cafes, the secular women events. These are helping us to stay connected. So if you're feeling disconnected or you haven't joined us for one of those, I really do encourage you to do so. Again, you can find all that with Zoom links in our meetup room at meetup.com/CFL Freethought. You can also find us on Facebook as well, and that's at CFL Freethought. But you need to join Meetup to actually get the Zoom logins. So if you want to be able to be sure that your question is considered, come and join us on Zoom. We do try to monitor YouTube, but definitely we're following the questions that are popping up here in the Zoom meeting. If you're with us on the Zoom meeting today, please feel free to turn on your camera, but be sure that your microphone is on mute. Those of you in the Zoom meeting will find the chat option available at the bottom of the screen on your computer. And if you are on a mobile device, just tap the screen and it should appear as an option to chat. And chat is where we want you to ask questions today. So ask your questions, ask away, put those there, and we'll get to as many of them as we can. And with that, with all the housekeeping taken care of, I will introduce our special guest. Dr. Paul Halpern is a professor of physics and a fellow in the humanities at the University of Sciences in Philadelphia. He is a recipient of the Guggenheim Fellowship and a Fulbright Scholarship and is a fellow of the American Physical Society. He's appeared on the PBS series Future Quest as well as the NPR show Radio Times. Paul is a prolific author with 16 books behind him, and he joins us today to talk about his most recent book, right here, Synchronicity, the epic quest to understand the quantum nature of cause and effect, which was just released and is available on Amazon and other fine booksellers everywhere. So Dr. Halpern, welcome to sunny Florida. We're happy to have you with us, and I will hand it over to you.
Thank you. I'd like to thank the Central Florida Freethought community for inviting me and for Jocelyn for the kind introduction. So I'm going to talk today a little bit about my recent book. In fact, I've been writing books for 30 years now. My first book came out in 1990. So this is the 30th anniversary this season of my first book, Time Journey. So it's been quite a long journey. So anyway, let me talk a little bit about my recent book. So the new book is called Synchronicity, the epic quest to understand the quantum nature of cause and effect. Well, that's a lot of serious words, but I'd like to kind of explain what is going on in quantum physics and how that relates to a term called synchronicity, which was coined by Carl Jung. So let's start off with somebody who's familiar to everyone, Albert Einstein. And Albert Einstein heralded a revolution in modern physics in the early 20th century. He's known famously as the father of relativity, both special relativity and general relativity, which revolutionized the idea of space and time, showed that space and time are part of the same entity, that one could be transformed into the other, and also that energy can be transformed into mass. His famous equation, E = mc squared, showing that if you have a clump of matter, you can turn that into energy, which is the principle behind atomic power. Einstein also, somewhat less famously, was one of the founders of quantum physics, he was one of the people who first worked with the idea of a quantum. Now, quantum just means quantity or small amount, sometimes used to refer to a parcel of energy or a little package of energy. So in the original incarnation of quantum physics proposed around 1900, it was an idea that energy is broken up into really, really small pieces. And that explained some experiments which weren't well understood at the time, justified them. And Einstein was well on board with that idea that energy can be broken up into small chunks. And that led him to what's called the photoelectric effect, that if you shine light on a metal, then you can produce electricity. And that effect is used in modern day electronic cameras, including cell phone cameras, digital cameras. So we thank Einstein for the part of the quantum revolution that allows for images to be captured electronically, which was pretty amazing. Now, Einstein, though, in the 1920s, he became rather critical of the direction quantum mechanics moved in. So from 1905, let's say, to the 1920s, he was all on board with quantum mechanics, and then something changed. And what changed is that quantum mechanics began to embrace the idea of randomness. And Einstein said he did not think that the good Lord, or as he said, the old one, plays dice. Sometimes that's quoted as God does not play dice with the universe. Now, by God, Einstein meant, in a sense, nature. He meant the laws of physics. He was not a believer in a personal God, but rather he believed that nature had a kind of an optimization, that there was some drive in nature toward the best of all possibilities, the ideal possibility, and that nature was constrained by certain ideals like cosmic beauty, elegance, and so forth, and that the universe functioned in a way that made sense. So when Einstein said God does not play dice, he meant that nature would not throw dice, because that doesn't really make much sense. What makes more sense is that nature would follow smoothly, that everything would follow one step at a time, in a way that's deterministic, in a way that's mechanistic. So that's what Einstein believed. And he based his thinking on an earlier philosopher named Baruch Spinoza, also known as Benedict Spinoza in Latin, who said that in nature there is nothing contingent, but all things have been determined from the necessity of the divine nature to exist and produce an effect in a certain way. So what Spinoza was saying is that nature produces the optimal universe, and that if you try to change things, that you're not to get a suboptimal universe, that is not possible, because nature has a certain constraint on it to produce the best of all possible worlds. And Einstein said many times that his views of the divine, the views of the universe, are near to that of Spinoza. Admiration for the beauty of and belief in the logical simplicity of the order and harmony, which we can grasp humbly and only perfectly. So Einstein was a believer in the Spinoza's idea of a God constrained by the laws of nature and essentially equivalent to nature. Now, Einstein was not the first person to come up with the idea of a deterministic universe. Isaac Newton, well before Einstein, came up with the laws of mechanics, which, if applied, lead to a clockwork universe. And that was most aptly put by a thinker named Pierre Laplace, who said that if you know the positions and the speeds of everything in the universe at any one time, and you know all the forces on all the objects in the universe at any one time, then you can use the forces, positions, and speeds to predict the entire history of the universe. It's a bit like winding up a clock and this just letting the clock run. So everything should run like clockwork forevermore, because everything is determined from what happened before. So that's the deterministic or clockwork universe, which Newton believed in, and also Einstein believed in. He believed that everything must follow from prior times. Now, quantum physics, as expressed in the 1920s and 1930s, doesn't quite work that way. First of all, there are random elements, much to Einstein's chagrin. And secondly, much to Einstein's dismay, things can happen that are non-local. Einstein believed that everything should happen at a particular point, that everything should be affected by its neighbors, things that are directly impacting on it. But things can happen at a distance in quantum physics. There's a phenomenon called entanglement, where you can take two particles with a shared quantum state and you can separate them a long distance away from each other, even hundreds of miles away from each other in theory. And because they're still in the same quantum state, they're still sharing information. And if you try to measure the properties of one of the particles, then you instantly know the properties of the other particle. So that is non-local, and because quantum wave functions can persist for a long distance, an indefinite distance. So Einstein thought that that was very strange too. He did not believe in that. And he called that spooky action at a distance. He said, I cannot seriously believe in quantum mechanics because a theory cannot be reconciled with the idea that physics should represent a reality in space and time free from spooky actions at a distance. That's what Einstein wrote to quantum physicist Max Born. And he used the term spooky, which is very interesting. And that's because Einstein was not a believer in the paranormal. He was not a believer in psychic phenomena or the occult. But during the early 1930s, on a visit to California, he was constantly bombarded by information by people who were interested in psychic phenomenon, believers in the paranormal. And he had to refute that, or in a way sometimes turn down their invitations, or say, well, that's not really science. There might be another explanation for it. So Einstein did have encounters with people who believed in pseudoscience, and that might have made him think that you need to define physics in a way that it's above criticism. And quantum mechanics, he thought, did not meet that test, because quantum mechanics seemed to have things happening at a distance that appeared in some ways a little bit like paranormal influences. Now, they weren't really, Einstein knew it wasn't really that particles could read each other's minds, but Einstein felt that the fact that particles were supposed to communicate at a distance according to quantum mechanics was a flaw in orthodox quantum mechanics, and there must be another explanation. There must be something going on behind the scenes. It's kind of like if you go to some kind of demonstration of so-called psychic phenomena, then you find out that something's going on beneath the table, or there's a Confederate who's reporting on what's going on, or there's something going on behind the scenes. Well, that's what Einstein thought, that there was some way that quantum particles can communicate with each other discreetly, and that we're not seeing that, and that explained quantum physics, and that the standard explanation of spooky action at a distance was simply incomplete. And this famously made the news, New York Times headline, Einstein attacks quantum theory. He says that it's not complete. And that was because he published a paper in 1935 with two of his assistants, Boris Podolsky and Nathan Rosen, criticizing quantum mechanics, criticizing the idea of entanglement, and trying to find a way around it. Now, meanwhile, Einstein was far from the only person who believed in determinism. Determinism was a very popular belief in the 19th century and even forward into the early 20th century. So determinism means that things follow from each other. Cause follows, is immediately followed by an effect. So if you have an effect, you have a cause, and there's kind of a chain link fence that connects an initial cause with a final effect, that there's, or you can think of it as toppling dominoes. You topple one domino and the next domino topples and so forth, that everything happens deterministically. Well, this is something that psychologist Sigmund Freud believed, and also believed that if you could somehow scan somebody's mind at any particular time, you could predict their mental states in the future. Now, Freud believed that the early life determined the later life, and that that what you're thinking at particular times was set by your childhood experiences. So, for example, if you make a slip of a tongue, that's not accidental. That is usually intentional. That's what we call a Freudian slip. So, in this cartoon, a Freudian slip is when you say one thing but mean your mother. I mean another. So, if you say something wrong, it could be an indication of something going on in your psychic life that might be in your unconscious mind, that results from your childhood or from some experience you had, maybe a trauma that you had early on, in a kind of psychic determinism. And all these things are stored in the unconscious mind and surface in the conscious mind, which is only, in Freudian theory, the tip of the iceberg. So you have most of the mind is unconscious thoughts that, and sometimes they surface. Now, in opposition to the ideas of Einstein and Freud, let's look at another physicist, Wolfgang Pauli. His name is pronounced Pauli because he was from Vienna, Austria, a quantum physicist, and another psychologist, Carl Jung, who's from Switzerland. Now, Pauli was a very well-known quantum physicist, and he was sometimes known as the second Einstein. Now, in German, the word eins means one, zwei means two, so sometimes Pauli was called Zweistein, which means two stones instead of one stone, kind of a joke on Einstein's name. But Pauli was a kind of wunderkind, or child genius. When he was only age 20, he was asked to complete a definitive account of relativity, and he understood it really well and published a book chapter that was an amazing account of relativity and won him a lot of fame as a very brilliant physicist. Now, Carl Jung was a follower of Freud, a disciple, but then he decided to set off in a new direction. Instead of Freud's idea of a single unconscious, which in Einstein's language would be known as local realism, something that happens internally, he believed in a collective unconscious, which is, if we look at a physics analogy, that's a little bit like quantum entanglement. Some things that are happening simultaneously over a wide range, over a wide space. And the collective unconscious is not just one person, but unconscious that is associated with the human race, and not just localized in time, but extending to all times. So extending to all spaces, all times. And that has a connection with relativity, because Jung was interested in the idea that relativity looks at all of time and all of space as a unity. And there's also an idea in Jungian psychology of archetypes, which is the idea that certain images can be resilient and transferred from culture to culture. So ideas from ancient Egypt might still be present in our own minds, according to Jung. Now, Jung coined the term synchronicity around 1930 in reaction to modern physics. Now, in the 1910s, Jung got to know Einstein to some extent. They had dinners together because they both lived in the city of Zurich. Jung spent most of his life in Zurich. Einstein was in Zurich for a couple of years after he got his PhD, and he worked in a patent office for some time. And then once he became a professor, he worked in Zurich at 2 different institutions and had dinner with Jung several times. And that led Jung to an appreciation of the idea of flexible space and time, and maybe even the idea of faster than light connections, meaning connections that happen simultaneously rather than taking time. Because if something is slower than light, then it takes a certain time for an effect to follow a cause. But if something is faster than light, you can have an effect that happens at the same time as a cause or even before a cause. So you can have acausal connections, which is what synchronicity means. It's an acausal connecting principle. Now, Pauli in physics was known as very hard-headed, very stubborn, but he also had a sensitive soul, which he didn't let out very much. Most physicists found them exceedingly brilliant, but also extremely critical of others. At a seminar, if somebody was giving a talk and he was sitting in the audience, he would find brutal criticism of the speaker very often. And people would quiver because they didn't know what he would say. He would bash the person who was speaking. He would bash others. Even famous physicists such as Einstein, he would poke fun at. And one of his famous criticisms was he once said that something was so incorrect that it was not even wrong. You couldn't even say it was wrong. It was beyond wrong. But Einstein respected him, and Einstein would send Pauli his theories. Pauli would critique them. Einstein would usually protest, but sometimes he would say, "You were right all along, you rascal," and he would admit that Pauli was right after all. What Pauli was famous for, and what won him the Nobel Prize, is, first of all, he invented the idea of a particle called a neutrino, a lightweight particle that is neutral, and it was discovered years later. But the citation for the Nobel Prize was for something called the exclusion principle. That says that 2 particles of a certain type can't be in the same quantum state at once. They can't share a quantum state. It's kind of like a stadium where everybody has to have their own seat. You can't share a seat in the stadium. And certain particles are like that. They have to have their own seat. Well, that means that if you take 2 electrons of the same energy, they can't be in the same quantum state. So there has to be something different about them. And that difference is something we call spin. Now, spin does not mean standard rotation, but we can think of it that way. It's kind of an analogy. We can think of electrons as spinning tops, and we can think of them as spinning 2 different ways, either counterclockwise with the axis pointing up or clockwise with the axis pointing down. So if 2 electrons are together, one of them has to have an axis pointing up. The other has to have an axis pointing down. But unless you look at the electrons, you don't know which is which. So if you put 2 electrons in a box, each of them has an equal chance of being either spin up or spin down. So that's the Nobel Prize winning work that Pauli was famous for. Now, you have an interesting situation with entanglement with 2 particles of opposite spin. So suppose you take 2 electrons, put them in a box, and you know that one of them must be spin up and the other must be spin down. And then you separate them widely. You separate them, let's say, tens of miles or even hundreds of miles. And then you still don't know, you don't measure them, you don't know which is spin up and then which is spin down. And then suddenly you take a measurement of one of the electrons and you find that it's spin up. You instantly know that the other is spin down. Now, the opposite, if you measure the first electron as spin down, you instantly know that the other one is spin up. There's no question about it. So somehow that information is stored in the whole quantum state, which could range tens of miles, hundreds of miles, hypothetically even millions of miles. Experiments have been done showing that this property exists, that information can be stored in a quantum state that is separated a great distance. And this is a living example of spooky action at a distance. Pauli saw this as a truth, and he saw this as the fact that acausal connections exist in nature, and they exist through symmetry or asymmetry. Either two things are exactly the same or two things are exactly the opposite of each other. In this case, they must be exactly the opposite of each other. Now, if you have entanglement, the question is, can information travel faster than light? Well, if information is stored in a quantum state, then that information persists in a way that it could be shared faster than light. But if you start off with some information, if you start off with a message and you want to send it, that message can't be sent faster than light. So it depends on whether something is prepared in a quantum state already, so it already has an existing quantum state, or if you start something going, start a message going, then the quickest it could travel is light speed. You couldn't send a message faster than light. Now, the speed of light is something that's well known now, but as I show in my book, in ancient Greek times, there was a big debate going on whether or not light was instantaneous or took some time. For example, the Greek philosopher Empedocles said that light took time to travel through space, but Aristotle thought that light was instantaneous. So Aristotle wasn't always right. In fact, he was wrong many times in his ideas. And unfortunately for science, Aristotle's works were the main source of information about science for many, many centuries. So people didn't start considering the fact that light takes time until the Renaissance era, and then people such as in the Enlightenment, such as Galileo, who began to look at the question of whether or not light takes time. And this image is of an experiment proposed by Galileo of two people on two different hills, flashing lanterns and measuring the time it takes for the lanterns to flash to try to measure the speed of light. Galileo can never get that experiment working, but he proposed the experiment. And then years later, Albert Michelson and others came up with precise measurements of the speed of light. And the speed of light, according to physics, is the maximum rate of conveying information. So acausal connections don't have to do with information transfer, they have to do with sharing information, and they can happen faster than light, but information transfer must happen at light speed or slower. Now, let me talk a little bit about what happened in Pauli's life. So around 1930, he had some tragedies in his life, and those drove him to therapy, and that's when he met Carl Jung. So in the late 1920s, first of all, his father had an affair, and his mother committed suicide because of the affair. And then he got married to a cabaret dancer, but the marriage lasted only 1 year because she was in love with a chemist. And Pauli was very upset because he said if she had taken a bullfighter, he would have understood, but why would she replace a physicist with a chemist? He thought that was crazy. He began to drink heavily after he found out about the relationship. His marriage fell apart. And then finally, he realized he wasn't very successful with his relationships. So he wrote to Carl Jung. Jung assigned him to an assistant, a female therapist, Erna Rosenbaum, because of the issues he was having with relationships with women. And she had him write down his dreams for months. So every night he would write down his dreams until he practiced writing down his dreams. Finally, once he was practiced, he wrote down his own dreams. And then finally, he shared his dreams with Jung himself. So he had 3 stages of his therapy, first with Erna Rosenbaum, then self-therapy, and then with Jung directly. And in the process, Jung got access to more than 1,000 dreams that Pauli shared. And a lot of these dreams had symbolism, numerological symbolism. Pauli began to believe in numerology, the significance of numbers. And for example, in this symbol, the world clock, which was one of his dreams, he had four people traveling in a circle in some kind of clock figure, and that circle was inside another circle on top of a bird. And that was one of his famous dreams that he shared with Jung. Now, Jung published these anonymously, so people knew that Jung had a patient who was a physicist. But then later, when they collaborated, everybody realized that the patient was Pauli. And the collaboration was a book that they co-authored with two parts. First part was about synchronicity, an acausal connecting principle. And the second part was about some work Pauli did examining two astronomers, one named Johannes Kepler and the second astronomer named Robert Flood, and their two interpretations of the universe. So this was published, and people saw that the two of them were associated. Pauli helped Jung develop a famous diagram called the quaternio diagram, and they both felt that 4 was kind of a magic number in their numerological quest, that 4 was very important. And here we have 4 different things. We have energy, which is opposed to space and time. That derives from quantum physics and relativity, where there's a connection between energy and space and time. And causality, which is things that happen at the speed of light or less, or greater than the speed of light, rather. At the speed of light or slower than the speed of light, I should say. Or synchronicity, which are acausal events that could happen at any rate. So, and these 4 elements are a way of describing the universe, according to Pauli and Jung. Now, Jung also thought that synchronicity applied to meaningful coincidences, as he put it, in real life. For example, he had a patient who had a dream about a golden scarab, and after the patient related the dream to Jung, Jung suddenly saw an insect at the window pane, and Jung thought, oh wow, that's strange, that insect is a little bit like a scarab, and he thought it was a rather odd coincidence, and he recorded it and would relate that to give an example of synchronicity. Now, that said, that is not a very scientific way of coming up with a link between events. Quantum entanglement involves taking careful measurements and using mathematical theorems to try to establish a remote connection. Here, the remote connection is just something that's anecdotal. So this was anecdotal evidence. For scientific evidence, you would need to have an objective researcher recording such incidents and applying statistical methods to detecting whether or not there was a connection. Now, Pauli believed in a type of synchronicity which was called by others the Pauli Effect. And the Pauli Effect was the fact that he was a theoretical physicist and he had a penchant for destroying lab equipment. So you can't have Pauli in a lab, was the conclusion of other physicists. He would break the equipment. And it was not only when he was in the lab, but also if he was passing near the lab or even going through the same city. So one time, famously, he was in a train station in the German city of Göttingen, and simultaneously, equipment at the university suddenly exploded for no known reason. There's another time he was passing through Princeton and their cyclotron caught on fire suddenly that burned for more than 6 hours. So people started saying, don't go to our labs, don't go to our cities, stay away. And that was the Pauli Effect. Now, in 1948, Jung opened his institute, a center for teaching his method of psychology, located in a beautiful building in a lake near Zurich. And he invited Pauli to attend the opening ceremony. But suddenly, during the event, there was a loud crash. Without warning or apparent reason, a beautiful Chinese vase suddenly dropped off a shelf, smashed into smithereens, and released a huge puddle of water on the floor, flooding the floor. Pauli immediately thought it had to do with his effect. And also the fact that he was studying an astronomer named Robert Flood, and there was a flood caused, he thought that that was a too much of a coincidence, that it was an example of synchronicity. And he wrote to Jung to that effect. Luckily, the Jung Institute remained intact, didn't burn down, nothing happened to it. I visited it last year around this time, and it remained a delightful place, beautiful location, and it's very close to Jung's lakeside home, where he met with Pauli and many others for his therapeutic methods. And I saw the office where he met with many of his patients. And you can still visit it if you go to Zurich and take a train to the town of Küsnacht near Zurich. You can visit the home. You just have to make an appointment. So their correspondence continued to around 1957, and Pauli died in 1958. But before then, Pauli started to become more skeptical. He wrote to J.B. Rhine, who was a researcher in paranormal phenomena, expressing doubts about psychic phenomena. Rhine didn't get the letter until after Pauli died in 1958. Now, an odd coincidence about Pauli's death is his hospital room in which he died had the room number 137, and that number has significance in physics because it's the approximate inverse of an important constant in physics, which is approximately 1/1/37, 137. Now, what we might learn in conclusion from synchronicity is that in quantum physics, acausal connections are important. So it was great that Jung and Pauli pointed that out, that acausal connections are as important as causal connections. It's something we need to continue to investigate. And it's an open question why some connections in nature are causal, why some are acausal. Why can quantum states persist for very, very long distances, but other things need to travel at the speed of light or slower? So it's kind of a mystery. And coincidences, on the other hand, might be chalked up to things that are statistically very likely, and the brain's way of finding patterns in nature. So the human brain is always looking for patterns. So if you get several types of sensory input, you might make a connection. For example, if you go to a certain building, and in the building you're always hearing a certain humming noise, let's say from the pipes or something like that, you might start to associate that with the building, and you might feel that they're linked. Well, you might also connect hearing certain words in a song. Let's say you're listening to a song and then seeing the same words in print sometime later. Your brain might pick up that pattern when it might not normally have noticed it. So you might say, oh my gosh, synchronicity, what a coincidence. But it's the fact that statistically such things are likely to happen given enough people, given enough time. It's very likely that things like that happen. An example of something that seems improbable but is very likely is the birthday paradox. If you have more than 23 people in a room, there's more than a 50-50 chance that 2 will share the same birthday. Now that seems kind of ridiculous to have 25 people in the room and think that 2 must share the same birthday, but it works out according to statistics. So some things that we think are improbable turn out to be likely after all. So the lesson is always use scientific methods, apply statistical analysis. Whenever you're examining a phenomena, use objective criteria, large sample sizes, and apply that, and then you can start rendering scientific judgments. So I'm going to stop here and leave some time for questions. My book is available. You can get it on any online bookseller. You can get it on Amazon, Barnes and Noble, bookshop.com, IndieBound. And I recently signed some copies for a bookstore called Main Point Books. So if you order through them, not to plug a particular bookstore, but they have personally autographed copies. But if you buy a book and you want it autographed, you can send me the copy with a self-addressed stamped envelope. And as long as you have the postage, I'd be glad to sign it and return the book signed. So that's another way of getting a signed copy. So I hope you check out the book. There's a lot more about synchronicity, quantum physics, the history of the search for connections in the book. So I'm going to stop here and leave time for questions.
Thank you so much. This is such a broad sort of topic for I'm trying to think about all these different questions I have, because I think about, for example, I'm going to say for myself, I'm hearing you talk about patterns and the Pauli effect and destroyed labs. And then I think, well, that's just somebody who's seeing a pattern because they've now thought about it. And so they're looking for it. And I don't believe that. That's my skepticism kicks in. And I'm surprised to hear that scientists were believing it. I tend to think of them as not being into mysticism and numerology and ancient symbology. Do you find that scientists buy into this as much as the regular public?
So it depends on the scientist. There were actually, in the 19th century, scientists who, for example, a scientist named Zollner, who will look at psychic phenomena and try to come up with scientific explanations. Like there's a famous case of a quack named Henry Slade who did something called slate writing. He would take a slate and he would put it under a table, and mysteriously writing would appear. And this is he did this using like magic tricks, so people wouldn't believe it today. But Zollner wrote a whole book about how Slade had access to the fourth dimension. He somehow could reach into the fourth dimension and pull things out and see people from the past. And there's always a handful of scientists who believe in this. And Pauli was skeptical about many things, but then he began to believe in some of this stuff. But then, as I mentioned, in his final year of life, he started to become skeptical again. But most scientists are very skeptical of things like that. So it's been, since the 19th century, it's been a minority of scientists who bought into that kind of stuff. And the majority of scientists are usually pretty hard-headed and skeptical.
That makes sense. That's kind of how I would think of it. One of the things I read in your book was that Einstein talks about looking at a compass at a young age and the impact it had on him. Did you have a moment like that when you were growing up, and what caused you to decide physics was where you wanted to focus your work?
That's a good question. I used to enjoy going to museums, and in Philadelphia, where I grew up, there's a great science museum it's kind of a push button museum, which is ideal for kids. So you can come in and just push the button and see what happens. So I would just keep pushing buttons and seeing what happened. And I was just fascinated. It was just like this other world, this other universe of science. And that sparked my interest. Plus reading a lot, and eventually reading a lot of science fiction, wondering about the universe. And then I happened to be good in math. Was my best topic. So I put them together, like science, was good in math. So that's why I went into physics.
Makes sense. So you tend to weave history and physics together in this book, almost equally in some ways. So what prompted you to decide to intersect these two fields together?
So I've always been interested, I should say, since I started writing books, in the intersection between physics and culture. So my first book was published almost exactly 30 years ago, Time Journeys, which looked at time from a cultural point of view as well as a scientific point of view. So that's become kind of my niche, my specialty, looking at the intersection between how scientists view the world and how philosophers, psychologists, artists, and so forth view the world. So I've also become friends with artists who are interested in science and musicians who are interested in science, and that shapes their work. And it's fascinating to see the interplay. And the direct reason I got into that was because my PhD thesis was very, very mathematical. And after writing that thesis and just doing math for a couple of years, I needed a break. So I was like, I want to do anything except math. And that's when I was invited to give a talk at the college I was teaching at about the nature of time. And I thought, great. And I just started reading about time from all different points of view, religious point of view, philosophical point of view. And, and that led to some of my books. And my career has continued from that point on.
That's time to me sounds like such a hard topic to try to even develop a talk on, but I don't have the background, but I can appreciate the challenge that would come from that. I want to remind everyone that if you're on YouTube to ask a question if you're watching this right now as well, because we are monitoring it. I did see a question from our people, the people watching. It says, if synchronicity is about seeing things you believe are linked, but are not, is it linked to a concept in psychology where the mind is fooling itself?
So, so synchronicity, in my view, has many aspects. So if we completely look at the science behind it, which I talk about in my book, you would have to say, okay, what is it based on? And it's based on the idea of acausal interactions. And then you say, okay, are coincidences in real life acausal interactions? Well, no one has really established that if for example, the famous case of dreaming about a scarab and then seeing a bug on a window, no one has ever showed that, okay, there's some link between the two of them. Rather, you say, well, okay, statistically, there is a chance that something like that will happen eventually. Just like statistically, if you wait long enough, things like that will happen. There are going to be things that seem like meaningful coincidences, but really are not meaningful at all. So what I would say is Jung's full definition of synchronicity, yes, it does include, as he meant it, meaningful coincidences, but he also recognized the value of science. And Pauli certainly recognized the value of science. So if we were to explore the phenomena scientifically, we would have to say, okay, let's do a study of thousands of people and monitor them. I don't know who would agree to this. You would have to go through what's called human subjects. You would need to have people agree to be monitored all the time. They'd have to be monitored full time and then look at, what are the odds that these coincidences come up in real life. And my feeling is that statistically there wouldn't be any real correlation that transcends what you'd expect by mere chance. Whereas paradoxically, in quantum physics, yes, you have correlations that are happening all the time in quantum physics that transcend mere chance, that are well established. So you do have acausal connections in quantum physics. Now, what that says about the mind is an open question. Some people think that you can use quantum physics to try to explain the brain or try to explain the mind. And that's an area, a frontier area that's under development. It's not something that has been explored in a very methodical way, in my view, but it's more of a hypothetical idea that maybe quantum physics can explain the workings of the mind.
Okay. So this kind of ties into something I was thinking about, which is you talked about information being stored and causal, and that it can be faster than light speed, correct? I think that was something that was referred to midway in your presentation. And I'm trying to understand from a non-scientific background, how does that really work? So you have the electron going upwards and the electron going downwards, and as you take them apart, and you can know what's going to happen, and the information is stored. That's what I understood you to say, correct?
So it's a mystery, because what is real in quantum physics is a quantum state. So the particular particles are not the real things in quantum physics. What's real is a shared quantum state. So you can talk about what happens to the quantum state over time. And then when you take a measurement, you're measuring an aspect, a facet of the quantum state. So that quantum state is if you have a case of entangled electrons, that quantum state can be miles long.
Okay.
So it's, I mean, imagine, a really, really, really long train, and imagine somehow freezing the train so that if you tap on one side of the train, let's say you tap on uh, the caboose, and then you have the engine car. You tap on the caboose, the engine car would immediately move, because the train is so frozen solid that it immediately moves. Now, that's not what happens in real life. You have like a wave going through, and that wave is going to take less than, or it's going to be slower than the speed of light. But in quantum physics effects, it's like you have everything frozen so that everything is moving in unison. And there are cases, technological cases, where we make use of that. There's something called superconductivity. Superconductivity happens when things are very, very cold. For some materials, rare materials, you have electricity that's moving in unison through a wire, and the electricity does not see any obstacle or impurity in the wire. So theoretically, you could have electricity being generated in a waterfall, like let's say Niagara Falls, and immediately, without losing any energy, without seeing anything, being transported down to Florida, along the superconducting cable, and not losing anything because it doesn't see the intermediate steps, which is pretty
Okay.
remarkable.
Yeah, I mean, it sounds remarkable. And asking, how do you take that and put it into a practical application? Have we gotten to a point where we can practically apply that to improving things? If I realize that's a kind of strange question, but that's kind of where I start thinking, how can we use this?
Well, quantum physics is applied all the time. For example, the idea of the transistor, um, computer chips make use of quantum physics, and then these things which are synchronized, like superconductivity, are used, for example, in magnetic levitation trains. So you have bullet trains that travel over superconducting magnets. And these magnets are perfect magnets. As long as you keep them at a certain temperature, they don't lose energy. Now you have to keep them very, very cool, very, very cold, but they don't lose energy because they don't see impurities, they don't see friction. It's kind of amazing. It's like skating on a perfect ice skating rink and not noticing that there are bumps, not noticing anything, and you just skate immediately across it without, any problem. And
I
that,
lived in Japan a few years. I've actually been on one of those trains. It's pretty
wow.
cool. It is. It's awesome. So how did you select? Let's go to something more mundane. How did you select the quotes to open the chapters?
Oh, sometimes I remember quotes, sort of comes to my mind, free association. Sometimes sometimes I get quotes from particular people that I like, and sometimes the quotes don't quite fit into the chapter, but they become standalone quotes. Like, for example, I had the pleasure of interacting with a well-known physicist, Freeman Dyson. And Dyson was an amazing physicist. He just recently died in his 90s, but he remembered the 1940s very well. He remembered interacting with Pauli and people like that. So he was this incredible resource. And when he was alive, if you emailed him, he would email back like almost immediately with these very short, snappy answers. And I liked it because they're really nice for standalone quotes. So I took some quotes from people like Freeman Dyson to head the chapters.
That's
But
sweet.
yeah.
We have a question. Can you explain the relationship between superconductivity and action at a distance again?
So action at a distance, that's an old term, and that applies to whenever you have a force that can be conveyed over a distance. And Newtonian physics actually imagined that the sun's gravity affected Earth instantly. And then later, Einstein showed that that's not the case, that Earth's gravity, the sun's gravity is conveyed at the speed of light towards Earth. So if the sun blinked out, it would take time for Earth to notice that the sun disappeared. It would take, in fact, 8 minutes, and then Earth would start moving in a straight line instead of orbiting. So gravity generally moves at the speed of light, but it used to be thought that gravity was action at a distance. Now, spooky action at a distance, as defined by Einstein, is this idea of entanglement, of things affecting each other immediately. So having one electron affect another electron. And the way superconductivity works is that electrons pair up. So electrons form pairs called Cooper pairs. And these pairs have one is spin up and the other spin down in each pair. So they form couples, okay? But once they form couples, then they no longer obey the exclusion principle because they're couples. They don't have the same property. It's a little bit technical reason. And then they could all crowd together. So remember I said the exclusion principle is like a stadium where everybody has its own, every particle must have its own seat.
Yes.
But, that's for particles called fermions. Fermions are particles that obey the exclusion principle. But then there's another group of particles called bosons, and bosons do not obey the exclusion principle. And when two fermions couple together like that, one spin up and the other spin down, and they lock together as a couple, they act kind of like a boson. And bosons behave at an event kind of like being in a mosh pit, all smashed together as close as possible. So that's what the electrons do. They smash together and form like a pulp of electrons that move in unison. So they move lockstep because they act like a whole bunch of bosons moving in lockstep.
Okay. Second part to this question is, how does the lack of resistance in superconductivity relate to the instantaneous information exchange in entangled quantum states?
Well, that's because this superconducting state, it's called coherent, which means it's resilient. Nothing can stop it. Once the state forms, it doesn't really see any, it's not really physically located in one position, so it doesn't really see anything in between. So it's basically ignoring everything, all impurities, all resistance. It's traveling in unison, in bulk.
Okay. All right. You tweeted on July 29th.
Oh no.
Well, I went and I was looking at your Twitter account, and it said, this is Albert Einstein quote, "I am happy because I want nothing from anyone. I do not care for money. Titles or distinctions mean nothing. I do not crave praise. The only thing that gives me pleasure apart from my work, my violin, and my sailboat is the appreciation of my fellow worker." You shared that on the 29th. Do you feel the same way? Do you feel that way about where you are in your work, and have you reached a point where you're just enjoying what you do, or what's next?
Well, I do believe in the idea of avocations or hobbies. So I remember I had my first semester of college, I had an English professor, and he was very casual. We chatted a lot. And one of the things he told me is always have goals that are not your main goals, that are secret goals in a way, that so that if your main goals fall through, you have these other things to fall back on that are non-competitive goals. So you're basically just competing with yourself. So I remember that when I was in graduate school, because I was really heavily involved in mathematics, and I felt like a walking, living zombie, um, trying to work on my PhD thesis, because I was just working on these equations, and I was just working on the computer and writing and doing all these things and kind of isolated. And then I started to feel like, hey, wait a minute. I thought there was more in life than this. And then that's when I heard about, at the time, a coffee house, which was basically a poetry slam. And I thought, hey, when I was an undergraduate, I tried my hand at rather bad poetry. And I thought, well, maybe I can try that again. So I went to these events and wrote poetry. And it was really therapeutic because I was doing something I wasn't really sharing with anybody at the time. And I was writing this poetry and sharing it to others in this coffee house event. And then finally, um, we had my department had a Christmas party. It's actually a St. Nicholas Day party because there were a lot of Dutch people there. So it wasn't exactly Christmas. And they had a contest for best poem. And I wrote this poem about the professors in the department. And we had this really bad, clunky elevator that was always out of service and doing all these crazy things, wobbling and doing all these things. So I made up a poem where the elevator would respond to each physicist in the department according to their research. Like one who was studying chaos, it would go chaotically, and it would do different things. And unfortunately, I lost the poem because I did it on a computer at my university, and I printed out one copy, and then I shared the copy during the party, and it was posted on a wall in the department, and then someone threw it in the trash at some point. so,
Oh,
so I don't have the poem. I still remember it, and I don't have access to that computer because it was an old style computer. But anyway, that was really uplifting to win that contest, because up to that point I thought, well, I'm just kind of an okay graduate student. I'm getting my PhD, but other people are publishing more and so forth. So I stopped comparing myself to others and thought, well, I'm the poetry guy. And then once I got out of graduate school and started to do something different, I thought, well, maybe I could try writing something, not poetry because it's not that good, but try writing books. So that's when I wrote my first book. Now today, back to philosophy, my philosophy is to have hobbies that I keep to myself and I measure myself against, so that I fall back on in case like something goes wrong, like all of a sudden, you know,
I
I find
understand.
out that my book's not selling.
No, it's I agree. I think we need to have a variety of different things in our lives. It allows for us to decompress also and think about those other things because we're not actively working on it. I find that that's helpful as well. Um, you have in your book on page 86, you wrote, if the physicists knew what was about to come, they'd either toast with a bubbling champagne or down to a stiff whiskey, depending on their philosophical perspective. And I read that and I made a little note to myself and I said, well, which philosophical perspective, chooses champagne and which one's choosing the whiskey? I was just curious, and it's more of a joke, but I wondered if there really was something about those two drinks that caused you to write it like that.
Well, I thought, well, one of them is drinking champagne is usually like, I was talking about the New Year, is usually like a celebration drink. And drinking whiskey, sometimes Not always. I don't want to knock whiskey, but sometimes people who are sad about something might say like,
Ah,
"Oh, I'm going to take a swig of whiskey." So it depends on whether they were happy that there are these flaws in determinism and the past picture, which called for new physics. Now, some people are very happy with physics being exactly the way it was and not having anything new. And some people always like novelty. Like, for example, today there are experiments being done at the Large Hadron Collider in Switzerland. And the experiments seem to be confirming the standard model or the old model of physics. But a lot of people say, hey, wait a minute, what about coming up with new theories? So people who want to come up with new theories have been very disappointed. So they might be the ones who turn to the whiskey rather than a champagne every time an experiment comes out.
I admit I'm not a whiskey drinker. I'm like, I would always choose the champagne, but yes, sad or happy.
I'm
Okay.
not advocating these things.
No, I know. I admit I don't have the background to be able to really dig into questioning the science as much as asking fun questions about the language that you've chosen in
That's
the
fine.
book. Well, we're kind of reaching the end, but I did have a question, which is, how can history inform science today? Like, what would you want? Would you want the people that are going into science today, the PhD students today, to be also doing research and understanding of history? Like, do you feel like that needs to be something that should be running with it, or can it just stand alone? We study science only.
Well, at the very least, it's important to know about previous ideas so that you don't reinvent the wheel, so to speak. There are cases in science where people thought they came up with an original idea, and then all of a sudden they get a letter or an email from someone and say, hey, wait a minute, I came up with that 20 years ago. Didn't you read my papers? Now, it's easier today with Google searches, or should be easier, to find something that's been done before, but there's also a lot of material out there. So one has to be really careful. But also, we learn from history that scientists are flawed, that almost every scientist we study has some flaws. I mean, Einstein was notoriously not very nice to his first wife, especially toward the end of their marriage. So some people are like nowadays, like, hey, let's cancel Einstein. He was a creep. Look at his. I see that on Twitter. Some people, I post something about Einstein and said, look how he treated his first wife. You can't say anything nice about Einstein. But on the other hand, he was a great humanitarian. He rescued all these refugees during World War II. So things are balanced. And then you look at physicists who you say, oh, they seem like nice people, but then you find out that they had all these other strange personality quirks. Like Niels Bohr was this great family man, but then when he spoke, he muttered when he was talking, and he couldn't really understand what he was saying. So you kind of had to you know, um, just kind of imagine what he was saying. So it made him seem more enigmatic
Ah,
because people couldn't understand what he was saying very well. And then he was also really absent-minded. So incident of that is one time he was at a podium speaking, and he accidentally pushed the button that lowered the podium into beneath the stage, and he kept talking. And since people weren't really understanding him anyway, they're like, oh, this is kind of strange. And he
yeah.
didn't notice at first.
It's kind of theater, actually. It turns it into more of a theater if he's
Yeah,
moving like that.
yeah. So that Bohr was a quintessential, one of the nicer people, had a happy marriage by all accounts. So we could
Yeah.
only talk about the physicists who were nice people, but that would narrow it down
Well,
considerably.
well, that's I think a good note for us to kind of end on. So you said your classes are back in session. We had a question from YouTube. They didn't hear us talking at the beginning. So your classes are back in session and you're meeting in small groups. That's correct?
Well, my university's undergoing a hybrid model. So large classes are online. Necessary classes like labs where you need hands-on experience, like you're working with doing dissection or something like that, that's in person. And then my classes are small seminars, and that's optional. So some people are choosing to put those online, and I personally like coming in with a mask, with social distancing and all those things, and coming in and teaching. My students all wear masks, and it's only 4 students to the room, which normally holds 20 people. So, and they spread out. So it seems very safe. We're being very, very careful.
That makes sense. I have a 17-year-old and he's taking all of his classes online. And I can say that he would be better served if he was in a situation with 3 other students and 1 teacher. I think he would probably be more focused than trying to listen to it online.
I'm
Um,
happy to
I-
be back teaching
it,
in person, but
it's hard because of the safety. But anyway, well, we all know where COVID is. We don't need to talk about that. We'll talk about, this is the book. Everyone should get a copy. There it is. Thank you so much for coming and spending your afternoon on Sunday with us. We very much appreciate it. It's been wonderful to have you here.
thanks for the invitation. I really enjoyed this.
Thank you.